students. Before we begin with today's class, again let us recall what are the topics that we have covered in last class. The first thing, we started off with the new chapter called Biomolecules, and we discussed about what are biomolecules, and we listed out some of the important biomolecules that we are going to cover in this chapter, and they are carbohydrates, proteins, vitamins and nucleic acids. And then we started off with carbohydrates, and carbohydrates are defined as the optically active polyhydroxyaldehydes or ketones or compounds which produces such units on hydrolysis. And we discussed about the optically active compounds as well. And then we had the classification of carbohydrates, which can be done in 3 different ways. The first one is based on the number of monosaccharides produced on hydrolysis. Under that we have monosaccharides, oligosaccharides and then polysaccharides. Monosaccharides are the carbohydrates which cannot be further hydrolyzed. Example is glucose and fructose. And oligosaccharides are the ones which produces 2 to 10 units of monosaccharides on hydrolysis. And then the polysaccharides are the ones which produces more than 10 units of monosaccharides on hydrolysis. Then the second way of classification was based on the reducing character. On that we have reducing sugar and non-reducing sugars. Now reducing sugars are the ones which reacts with Tollens and Valence reagents, and the non-reducing are the ones which does not reduce Tollens and Valence reagent. And then the third way of classification, that is based on the type of functional group present. Carbohydrates can have aldehyde as the functional group. In that case it is aldoses, or it can have ketone as the functional group, which will be ketosis. So that was about the classification of carbohydrates. Now out of monosaccharides, we are going to discuss in detail about glucose and fructose. And from oligosaccharides under disaccharides, that is carbohydrates which produces 2 units of monosaccharides, we are going to study in detail about sucrose, maltose and lactose. And then from the polysaccharides, we are going to study in detail about the cellulose, glycogen and starch. So these are some of the important carbohydrates that we are going to study in this chapter. And then we started off with the monosaccharides. Under monosaccharides, we discussed in detail about glucose, its preparation and its structure. Glucose can be prepared either by hydrolysis of sucrose or by hydrolysis of starch or cellulose. And then coming to the structure of glucose, we discussed the 3 different ways of writing the structure of glucose. The first one is open structure, the second one is cyclic structure, and the last one was Haworth structure. So till that we are done with glucose. Now coming to the second monosaccharide, that is fructose. So in today's class we are going to study about fructose, their preparation and its structure. Now fructose has the molecular formula of C6H12O6, and it is a levorotatory compound. That is, it rotates the plane of polarized light towards the anti-clockwise direction, and it contains ketone as the functional group, levorotatory ketone as the functional group, and it has a molecular formula of C6H12O6. Now coming to the preparation of fructose. Again, fructose can be prepared by the hydrolysis of sucrose. Sucrose is C12H22O11. Now C12H22O11, that is your sucrose. This on acidic hydrolysis, H2O H plus, you get C6H12O6 plus C6H12O6. This is your alpha D plus glucose, and you get a beta D minus fructose. So this is one way of preparing fructose from sucrose. Sucrose, which is again made up of a unit of glucose and a unit of fructose, on hydrolysis give back the monosaccharide glucose and fructose. So this is about the preparation of fructose. Now let's move to the structure of fructose. On the structure of fructose, first let us write down the open structure of fructose. C6H12O6. It contains ketone as the functional group. Now open structure, again from the different experiments conducted, it was found that all the carbon atoms are in a straight chain, 1, 2, 3, 4, 5, 6. The first and the sixth, that is 1, 2, 3, 4, 5 and 6. The first and the sixth carbon atom are found to have a primary alcohol. In the case of glucose, you have aldehyde on the first carbon and primary on the sixth carbon atom. Whereas in the case of fructose, you have primary alcohol on both the first and the sixth carbon atom. And the second carbon atom bears the carbonyl group. And then you have to arrange the OH and the hydrogen group. Now in this case, this carbon third will have OH on the left-hand side as usual. And your hydrogen, then you have OH, OH, and then H, and then H. Now this is the open structure of, you have OH on the right hand side, therefore this will be deep fructose, or I'll just write fructose. Open structure of fructose. Now if I write down the cyclic structure of this, in the case of cyclic structure, what happens is this OH on the fifth carbon atom will react with the carbonyl group on the second carbon atom. Now how does that happen is, if you remember from the glucose, this pi electron will shift and O will get a negative charge. On this negative charge, again hydrogen will come from here. Now this carbon will have a positive charge as this pi electron shifts. O with a negative, carbon will have a positive. Now this positive charge, this oxygen has got two lone pairs of electrons. Now this oxygen with a lone pair of electrons will come and attack, and it forms a ring with this carbon, fifth carbon and the second carbon atom. Whereas in the case of glucose, the ring is formed between the first and the fifth. Here it is between the second and the fifth carbon atom, because ketone reacts with alcohol. In the previous case, the alcohol reacts with the aldehyde, which is on the first carbon. Here we have carbonyl group on the second carbon atom. Therefore, C2 and C5 will form a ring to this oxygen atom. So if I write down the cyclic structure for this, 1, 2, 3, 1, 2, 3, 4, 5. Now what happens is, this second carbon, now this is your second carbon, will form a ring with the fifth carbon atom. And this will have CH2OH. Now this O is forming a bond with this carbon. In the process, it will have a positive charge. Now, in order to stabilize the positive charge, this hydrogen will leave, and this hydrogen will come and attack this oxygen atom, and it forms OH. It will form a OH. Okay, now I'll write it down over here. Now it forms a OH. This O will pick up hydrogen from here, forms a OH, and then you have CH2OH. And then this is your first, second, third, fourth, fifth, and sixth. Now third carbon atom bears the OH on the left hand side. You have your hydrogen, then fourth will have OH on the right, and then hydrogen, and then this hydrogen. So this is the cyclic structure. Now again, here also you have alpha fructose, beta fructose. Now that depends upon the position of OH on the second carbon atom. If OH is on the left, it is called as beta. So in this case, this is beta D fructose. If the OH is on the right hand side and this is on the left, then it will be called as alpha. Now let me write down the alpha structure for this as well. You have second carbon, third, fourth, fifth. Second, third, fourth, fifth, sorry. And then you have your sixth carbon, that is CH2OH. Now this second carbon forms a bond with your fifth carbon atom. Now in this case, OH will be on the right hand side, and then your CH2 OH, and then you have hydrogen OH, OH, H, and then this H. Now this is your alpha D fructose, where you have the OH on the right hand side. This is your first carbon, second, third, fourth, fifth, and sixth. Now you can see that the second carbon is forming a ring with the fifth carbon through this oxygen atom. When OH reacts with the ketone, it forms hemiketal compound. Hemiketal compound. Whereas in the case of aldehyde, that is in glucose, when alcohol reacts with the aldehyde of the first carbon, it forms hemiacetal. In this case, it forms a hemiketal compound, and hemiketal compounds are the compounds where you have C, and then you have R, OR, OH, and then one R. So in the case of, this is your hemiketal, whereas in the case of hemiacetal, you have R, H, and then OR and OH. In the case of hemiacetal, you have hydrogen, one R, OR, and OH, whereas in the case of hemiketal, you have two R groups. So in this case also, this is the carbon which has a OH group, and this is the R group, and this is the again another R, and then you have your OR. So because of this reason, it forms a cyclic structure. The alcohol reacts with ketones to form a hemiketal compound, which results in the form of a cyclic structure. So that's about the cyclic structure. Now let's move to the pivot structure of fructose. Okay. Okay, first I'm going to write down the Pivot structure of beta-D fructose. Now you can see that the ring is formed between 1, 2, 3, 4 carbon atom and 1 oxygen. That is, it is a 5-membered ring, whereas in the case of glucose, it forms a 6-membered ring. So in the case of 5-membered ring, you will draw like this. So 1 carbon, 2 carbon, 3, 4 carbon with 1 oxygen. It is again a 5-membered ring. Now what happens is, this will be the base structure. Now you have to arrange these groups on these bonds. Now whatever is on the right will come at the bottom. So on the second carbon atom, this is your second, this is your third, fourth, fifth. Now on the second carbon atom, you have this primary alcohol on the right hand side, therefore it will come at the bottom. So CH2OH. Now this is your first carbon atom, first, second, and you have OH on the left hand side, therefore OH will come on the top. And on the third carbon atom, now this is your third, you have OH on the left hand side, therefore it will come at the top, and this will come at the bottom. Similarly, on the fourth carbon, you have OH on the right hand side, therefore OH will come at the bottom and hydrogen will come at the top. Now this is your fifth. Now this group will again go at the top, so CH2OH, and then you have the hydrogen. Now this is called as beta-D fructofuranose. Okay, now furanose refers to the furan because it resembles the structure of furan, a 5-membered ring, furan. Therefore, this is also called as fructofuranose. It resembles the structure of furan. Now, in the case of alpha-D fructofuranose, this one, again, everything will be same. Only thing is you have to change the position of these two. So, in the case of alpha-D fructofuranose, you will have CH2OH on the top because glucose, you have it on the left hand side and OH on the right hand side, therefore it will come at the bottom, OH. And then you have this groups, same, OH, H, and then H, CH2, CH2, OH. This is alpha D fructose. So that's about the Havoc structure. The nala khari chungor na ba so fructose ki structure khande chungor me structure la china so mi ba open structure che cyclic structure che Havoc structure so glucose na chi sa hai ta di doubt ho rahi ne khebar khari ho na fructose ki na lo la carbonyl group di carbon ni ba la glucose ki na lo la carbonyl group di khol na carbon thangbo la ba di chi carbon thangbo dang na wa ni ki ma la ring di form che glucose na lo la fructose ki nalo la ring form che di carbon ni wa da ngawa ni ki mala khare china ketone na bi samala sula carbon ni boyo barwa ketone di khadi na terminal carbon sanding mara di chini de ki nalo la ring di carbon ni wa da carbon ngawa ni ki mala ring di form che le ani ni wa da ngawa ni ki mala chadi samala ani carbon thabo jerwa di sula li re CH2OH le Tadi nalo la carbon ngawa gi alcohol tang carbon ni ba ni ki ketone yam do react chini ngazo la hemiketal le compound che form cha wa le hemiketal de form cha gi yuza ngazo la khare cyclic structure the hemiketal la na khale chela la wala na carbon gi su la OR R ni OH yoga china dila hemiketal la gre hemiacetal la di sabala carbon gi su la R H OR OH na hemiacetal di glucose na che hemiketal di ketone na la che sorry the fructose na la ta this structure the ring na ta wala na chick ni sum shi carbon shi ta oxygen chick ta na shi dela ge carbon chick ni sum shi ta oxygen chick dus shine ko gi sobda le durwa daswa also glucose ki na la chot point khazula join chona point chok join chiwa digi na la chick ni sum shi na join chona kajina ring dinala member di nga che hagi nanola ring nanola member di kazure two in this amala sota guba tore ta di sota di nga so furan ki do yuza ko gi ni wala furanose la di fructofuranose ani furan gi structure do chi chi and di gala bond du chi and ni di group du jan di gala di won wa di du samala OH di ema la yudu samala ema yudu sama ko tore ya ga la tore ba eba yudu sama ko tole na wala dus chine carbon ni ba gana CH2 di a la yudu samala ko wala che OH di gana carbon sumba gana H di right la yudu samala wala che OH di gana carbon shiba gana OH di a la yudu samala wala che dene hydrogen di gana ani di khatu ina di gana li glucose ta chi par hai dus chine ani cyclic structure di Havoc structure le. So with this we are done with the monosaccharides. We discussed in detail about glucose and fructose. Now that we are done with monosaccharides, that is glucose and fructose, now let's start with disaccharides, which comes under oligosaccharides. Now disaccharides are the carbohydrates which produces 2 units of monosaccharides on hydrolysis. Di indicates 2. So under disaccharides we are going to study in detail about sucrose, then you will have maltose, and then lactose. So first we'll start with sucrose, then we'll go to maltose and lactose. Now under sucrose, we know that it has a molecular formula of C12, H22O11, and sucrose is a levorotatory compound, which means it rotates the plane of polarized slide towards the anti-clockwise direction. It is a levorotatory. Now sucrose on hydrolysis, C12H22 O11 on hydrolysis, that is acidic hydrolysis, it produces an equimolar mixture of glucose C6H12O6 plus C6H12O6 fructose. Now in this case, this is alpha D plus glucose, and this is beta D minus fructose. Now from this, it is seen that sucrose is made up of two monosaccharides, that is alpha D plus glucose and beta D minus fructose. Now let us form sucrose by joining together alpha D glucose and beta D fructose. Now formation of a bond or a linkage takes place between these two to form sucrose. Now we are going to do that. So for that, first you need to know the structure of alpha D glucose and you need to know the structure of beta D fructose. So first we'll draw the two structures. In the case of alpha D glucose, it is a 6-membered ring that we already know. So by now you should be able to write down the structure of fructose and structure of glucose. So in this case, I have a alpha D glucose, which is a 6-membered ring, and then you have a fructose, which is a 5-membered ring. Fructopyranose and glucopyranose. So in this case, each of this carbon will have a bond. Now this is the fructose, this is the glucose. Now it says alpha D glucose. Alpha indicates the OH on the first carbon atom is on the right hand side. Therefore, this is the first carbon. You will have OH at the bottom and H on the top. And this is your second carbon, third carbon, fourth, and the fifth carbon atom. Now on the second carbon atom, the OH is on the right. Therefore, it will come at the bottom and hydrogen. And then you will have third carbon atom with OH on the left hand side. Therefore, OH on the top, H, and fourth again have OH at the right. Therefore, it will come at the bottom. Hydrogen, CH2, OH, and then hydrogen. So this is your alpha D plus glucose. Okay, now coming to the structure of fructose, it says beta D fructopyranose. So beta means you have OH on the second carbon atom is on the left hand side, beta. So H2 OH will come at the bottom and then you have your OH. Now this is your second carbon, first, second, third, and then you have fourth, fifth, and then sixth will come here. So on the third carbon again, OH is on the left hand side, therefore it will come on the top, and then your hydrogen. On the fourth carbon atom, OH is on the right, therefore at the bottom, and hydrogen. On the fifth carbon atom, you have OH on the right, and then your CH2OH, which is the sixth carbon atom. So 1, 2, 3, 4, 5, 6. Now the linkage, a link is formed between these two monosaccharides in order to form the sucrose, and the linkage is formed between C1 and C2. C1 of glucose with C2 of fructose. Now in order to form the linkage between C1 and C2, if the arrangement is like this, then it is not possible to form bond between C1 and C2. Therefore, what is done is this structure will rotate by 180 degree so that this second carbon atom will come here and it can form a bond with this first carbon atom. Now for that, before the formation of the linkage, the 180 degree rotation of this compound or the structure takes place, and you will get a structure in which the second carbon atom will come here. So I'm going to draw that now. What happens is, on 180 degree rotation, you will get a structure like this, where this carbon will come here, and in the process, whatever is at the bottom will go at the top. So this CH2OH will come here. You need to remember this, and then OH, and then this carbon, hydrogen will go at the top, OH will come at the bottom. So this carbon is this one now. Now hydrogen goes at the top, and then you have your OH, And now this one, again, OH will go at the top, hydrogen will come down, so OH and then H. And this case, this one, OH will go at the top and then CH2OH. Now this is what you get after 180-degree rotation. You have second carbon atom over here now. First, second, third, fourth, fifth and sixth. Now what happens is, this will now react with this. Now I'm going to write this over here. Glucose, which is a 6-membered ring, 1 oxygen and 5 carbon atoms. And in this case it is alpha D plus glucose. So you must remember the structures of both glucose and fructose. Now alpha means again OH on the right, therefore come at the bottom. H, second carbon atom, is OH on the right, OH on the left, therefore it comes at the top on the first carbon atom, and then you have your hydrogen. And here the fourth carbon atom, OH on the right, therefore bottom, H, CH2OH, and then hydrogen atom. Now this is the structure of alpha D plus glucose, and this is the structure of beta D minus fructose. Now a linkage is formed between these two by elimination of the water molecule from the first carbon atom of the glucose and the second carbon atom of the fructose. So let me first number the carbon atoms. This is the first carbon, right at the bottom, first, second, third, fourth, fifth and the sixth carbon. Okay, I'm going to rub this now. Now what happens is, the linkage is formed between C1 of the glucose and C2 of the fructose. Let me write down the name here at the bottom. This is your beta D minus fructose. These two OH will react together and a water molecule is eliminated. And this two links through this oxygen atom, and you will get write down the same structure. Only thing is, this two will be connected through this linkage. The rest remains the same. Okay, let me quickly write down CH2OH, H, H, OH, and then you have your OH, H, and then OH, H, and then you have this hydrogen. And here you have CH2, OH, and then this OH, CH2OH, and then H, OH, and OH, H. Now this linkage is called as glycosidic linkage. Oxide linkage between two monosaccharides is called as glycosidic linkage. An outside linkage between two monosaccharides is called as glycosidic linkage. Okay, you need to remember this. Outside linkage between two monosaccharides is called as glycosidic linkage. Now, if you are asked whether sucrose is a reducing or non-reducing sugar, which is important, now in order to look for the reducing character, you have to remember that if a carbon carries an OH group, an OR group, an H or an R group, if a carbon is forming a hemiacetal compound which bears a OH, OR, and R and H group, if these three are present, then it is said to be a reducing sugar. Now in this case, you have to look for any carbon atom which bears these groups. So let us look at this carbon first. It has OH, it has OR, but it does not have a hydrogen atom, therefore this is not a reducing sugar. Similarly, on all the other carbon atoms, wherever you look, you will find that it does not carry all these groups, therefore sucrose is a non-reducing sugar. It is a non-reducing sugar. Now you need to remember this, it is important. Why sucrose is a non-reducing sugar? Because it does not, any of the carbon atoms in sucrose does not carry OH, OR and hydrogen atom. Therefore, it is a non-reducing sugar. One of the important terms that you need to understand under sucrose is invert sugar. Now, sucrose on hydrolysis, that is C12H22O11, on hydrolysis, it produces a mixture of glucose and fructose, that is C6H12O6 plus C6H12O6 fructose. You get alpha D plus glucose and you get beta D minus fructose. Now sucrose itself is a dextrorotatory. And this dextrorotatory compound on hydrolysis, you get a mixture of glucose and fructose, and glucose is dextrorotatory in nature, whereas fructose is levorotatory. So when you measure the rotation, this glucose has plus 52.5 degree, whereas fructose has minus 92.4 degree. So when you calculate the overall rotation, the levorotatory is more compared to the dextrorotation. Therefore, as a whole, it becomes a levorotation. So such mixtures or products which has a change in the rotation from the reactant, it is called as invert. There's an inversion in the sign of rotation. So this kind of products formed is called as invert sugar.